Good morning, students. Welcome to the class on Proton NMR Spectroscopy. In this class also, we will study the modal spectra of some examples. We will take some examples. We will try to predict the order of frequencies, then multiplicities, followed by their approximate delta values. For example, in this compound, as we know, because of anisotropic effect, alkene protons will give large delta value. So these protons will have high delta value. Then among these two, generally the carbon which is having more number of substituents will give low delta value. This should have high delta value, but this is only in this case. It is giving next highest delta value, and then so there may be little confusion between them. It's not a problem. We can predict them easily if we were given spectra. Then next will be this one, next will be this one. So when we know the order of frequencies, then we also predict the multiplicities. In this case, though this carbon doesn't have any alpha protons, but these two protons, they will couple with each other. They will couple with each other, so it gives a doublet with a, generally the J value for this coupling is very low. The J value for this coupling is very low. Next, this carbon, it also doesn't have any alpha protons, so it gives a singlet. Whereas this carbon, the protons have two alpha protons. So these protons have two alpha protons, so it gives a triplet. These two protons, they have 2 plus 3, altogether 5 alpha protons. So because of the 5 alpha protons, they will have, it exhibits a sextet, Sx. This methyl group, it is having only 2 alpha protons, so they will have a triplet. Now we can also predict the approximate delta values. Generally, alkene protons will appear between 4.5 to 6.5 ppm. Then allylic systems, they will appear around 2. In this case, I will give the exact values. It appears at 2.06. It appears at 1.7. Then D, so we can decrease the delta value further. Okay, it will appear at 1.45. It will appear at 0.8. So we can decrease the value further and further. Now when we try to draw a modal spectra, highest one, it is appeared at 4.75. It is a doublet because of the coupling between these two protons. These two protons will have a coupling. Of course, it is having weak coupling, so its value is 0 to 3 edges. It is a doublet. Then next peak is a triplet. Next peak is a singlet. Next peak is a sextet. 1, 2, 3, 4, 5, 6. And next peak is a triplet. 1, 2, 3. So this is how we can also draw a modal spectra when a compound was given. So it is a doublet at 4.75. It is a triplet at 2. It is a singlet at 1.7. It is a sextet at 1.45. It is a triplet at point A. Now we will take one more example and we will try to draw the model structure for this. This is N-butyl 1,1-chlorobutane. When we want to predict the order of frequencies, because this carbon is attached to more electronegative chlorine, yes, it will have highest delta value among all these protons. Now we know that inductive effect will decrease with distance. So next one will be this one. Next chemical delta value will be for this, and least delta value will be observed for this. Now we will try to predict the multiplicities. These two protons, they have two alpha protons. This side we have chlorine, but this side we have a carbon which is bearing two protons. So it is having two alpha protons. According to n+1 rule, 2 + 1, 3, it is a triplet. It gives a triplet. Now coming to these two protons, they have right side two alpha protons and left side also two alpha protons. So altogether we have four alpha protons. So according to n+1 rule, 4 + 1, 5. So it is a quintet, QT. It gives a quintet. Then this carbon, these two protons, they are having right side two alpha protons, left side three alpha protons. Altogether they have 5 alpha protons. So according to n+1 rule, it is 5 + 1, 6, sextet. The final methyl group, it is having only two alpha protons. So 2 + 1, it gives a triplet. Now we will try to predict the delta values. Now these two protons are on a carbon which is bearing chlorine electronegativity. So according to its electronegativity value, it will show a peak around 3.5 ppm. Now we know the inductive effect decreases with bond distance. Generally, these two protons, they will appear at a low delta value. They will appear at 2. And from here, the delta value will be even further lower. So this will appear at a delta value of 1.4. This will appear at a delta value of 0.9. We will also try to draw a model spectrum. So this is giving a triplet, then it is giving a quintet, 1, 2, 3, 4, 5. So I am writing these multiplets based on their ratio of intensities. Then this proton, it is giving a sextet, 1, 2, 3, 4, 5, 6. Then it is giving a triplet. So like this, we can easily predict the delta values, their order of frequencies, then the multiplicities when we were given a compound. Similarly, when we know the spectra and formula, we will also try to predict the molecular formula from the spectra based on its multiplets and then coupling constants. We can also predict the structure of the compound from proton NMR. Generally, please take the notes. Generally, NMR is used as a primary source of structural identification in organic chemistry. So whenever we synthesize a new compound or whenever we synthesize an organic compound, first we will get the proton NMR, then we will try to predict the structure from that. If we are sure that it is the required compound, then we will also take the other spectroscopic data like UV, IR, mass to complement the proton NMR. But as far as organic compounds is concerned, proton NMR data is the primary source of characterization. take this example and practice predicting the order of delta values, then multiplicities, and then approximate delta values. I will discuss a little bit about OH peak. OH peak generally it may be observed, may not be observed in a proton NMR spectrum. It is mainly due to the rapid exchange of alcoholic hydrogen with deuterium. We generally use deuterated chloroform as the NMR solvent. We use deuterated solvent, either deuterated acetone, CD3, CO, CD3, or deuterated DMSO, dimethyl sulfoxide. So we use deuterated solvent so that the spectra of these compounds will not interfere with the required compounds, because these are not having any protons. They don't exhibit any spectra in this region. Okay, so we can easily identify the given compound, right? So when we use deuterated solvents, then OH protons, it is sometimes it is possible to exchange with the deuterium. So when we exchange with the deuterium, we will get OD. So we don't observe any peak for OD, right? So for alcohols, sometimes we may get the peak or sometimes we may not get the peak. Even if we get the peak, we get a broad peak. We get a broad peak with very less intensity. Okay, right. At the same time, this OH peak, it is also useful in identifying the structure of the compound. No, it is used for exchange experiments. So a drop of deuterated water will be added to the compound so that this OH proton, it will be exchanged with deuterium. So the exchange is made faster either by using some temperature. When we raise the temperature, exchange may become faster, or due to the presence of small amount of an acid impurity. We can use some acid impurity to increase the exchange, or we can also use adding some water in the solution. So due to that, the OH proton will undergo rapid exchange with deuterium. When it undergoes exchange with deuterium, we don't observe any OH peak. So we can take two spectra without exchanging the deuterium. We will take one spectra, and after exchanging this OH proton with deuterium, we will take one more spectra. When we compare these two, we can easily identify which one is OH peak and where it is interacting. In the OH, if OH is present, we will get the peak. If OH is not there due to exchange, this peak will not be present in the molecule. So by comparing these two spectra, we can easily identify the presence of OH. At the same time, if it is interacting with the neighboring protons, that also we can easily identify. Right. Coming to this problem, what is the structure of this? As we know, alcoholic proton, it will have a very high delta value. Generally, it ranges from 1 to 8. If it is possible, it will give the highest delta value if it is present. If it is not present, we don't have this. Then this carbon, it is attached to oxygen. So these protons will have next highest delta value because oxygen electronegativity is 3.5. So later I will come to that value. We know the inductive effect decreases with distance. So C. and these two are chemically equivalent, so they will give the same spectra. Now it gives a triplet. If it gives a peak, it gives a triplet because it is having two alpha protons. If it exists, that means if it gives the signal in the proton NMR, it gives a triplet because it is having two alpha protons. Coming to these two protons, they have 1 and 2. They have two alpha hydrogens, so it will also give a triplet. Coming to this is having 2 plus 3 plus 3. So it gives a multiplet. 6 plus 2, 8. So it gives a multiplet. Sorry. Whereas this methyl group, it is having only one alpha hydrogen, so it gives a doublet. It gives a doublet. So this is how we can predict the multiplicities and delta values. We can also expect that chemical shift values. Generally, it ranges from 1 to 8 ppm. Mostly it appears above 4 to 5 or 6. Because this carbon is attached to oxygen, generally this will be observed at around 4 ppm, 3.5 to 4. Then of course, due to decrease in the inductive effect, these values will also come down. It is appeared at 1.8, it is appeared at 0.9. So this is how we can easily predict the proton NMR spectra when a compound was given. Take these practice problems and try to predict the approximate proton NMR spectra for these compounds. In this compound also, it will exhibit highest delta value, and then this, with the decrease in distance, inductive effect decreases. So next highest delta, next highest delta, and next highest delta. These two compounds are almost exhibit the similar proton NMR spectra. In this example, we do expect a similar spectra where it will give highest delta protons are nitrogen. Generally, they will appear between 1 to 5 ppm. Next highest will be this C, D. And I will also give the values. It appeared at 2.6, it at 1.75, this fellow at 1.4, this fellow at 0.9. You write the multiplicities, they are predictable. Okay. But what is important to know is sometimes this amine or OH peak, amine or OH protons, they appear with a broad peaks. So by looking at these broad peaks, we can easily identify that these belongs to either amine or OH peaks. You practice other details. This is of little bit importance in discussion. In this compound, aldehyde proton is the highest delta value. It appears around 9 to 10. Then protons which are next to carbonyl carbon, and of course see, these two are equivalent, so they will exhibit one spectrum. We also predict the multiplicities. Sometimes, the aldehyde proton may not couple with this, so it gives a singlet. It gives 3 plus 3, 6 septet. It gives a doublet. right? It is a low resolution instrument, but with high resolution we can predict, with high resolution instrument we can visualize the coupling between the aldehydic proton and the proton on alpha carbon. With a low resolution we will get a spectra like this: 1 2 3 4 5 6 7 and a doublet. So with low resolution we will get a spectra like this, low resolution. But when we look at the high resolution, it singlet, septet, doublet. But with high resolution, this peak appears as a doublet. All these 7 peaks, they will appear as doublet of septet. That means each and every peak, it will appear as a doublet, because there is a coupling between aldehyde proton and the proton on alpha carbon. But here the coupling constant J value is very, very low. So that is why in a normal low resolution instrument we don't observe this coupling. But in a high resolution instrument, say for example if you are doing this on a 60 megahertz instrument, we don't observe this. But if you are doing it on a 300 megahertz instrument, yes, we can observe this coupling. Of course, this doublet, it is far away from aldehyde proton, so it will not interact with this. So in high resolution also this looks like this. Then in the NMR spectrum, when we take the spectrum, we can also indicate the frequencies here. For example, the first frequency is 2894.6 and the second frequency is 2893.1. So on the scale, we predict the delta value. On the top, we can predict the frequencies. So when we write the frequencies, then it is easy for us to calculate the coupling constant. So just take the difference, right? So the J value is 1.5 hertz. So only in the textbook for problem practice, they will give delta values for these two peaks. Then we will be asked to calculate the J value in hertz. But in reality, when we take a NMR, proton NMR spectrum, we can also get the frequency values on the top, delta values, delta scale on the bottom, so that we can just take the difference between them so that we can easily identify the coupling constant. Now, this is the coupling constant for aldehyde proton. Now, this septet, it is also undergoing coupling with this proton. So here for each doublet, here the J value will also be 1.5 hertz, because this proton is coupling with this. Similarly, this proton is coupling with this. That means the coupling constant of this doublet or this doublet, any doublet of this septet, it will be 1.5 hertz. So from this we can clearly say that this proton is interacting with this. So based on the coupling constant values, if the coupling constant values are matching and the splitting pattern is matching, then we can clearly say that these two protons are coupling with each other. You just work out for this problem. And I will give one more problem. Yeah, I will give the delta values. It is attached to oxygen, so it will be highest delta. It is next to carbonyl carbon, so it gives the next highest. then C. Of course, these two are chemically equivalent. They will give the same signal. Here also carboxylic acid proton will give highest delta. Then these two are chemically equivalent, so they will give the same peaks. B, and then it is C, it is D. Now, if you want to know the exact values, this proton is having 2 alpha protons, it gives a triplet. This is having 3 plus 1 4, so it gives a quintet. This is having only 2 protons, so it gives a triplet. Triplet, quintet, and triplet. Right. For example, sometimes it is not possible to fit the delta values beyond 10. So that time what they will do, they will record the spectra, they will cut the spectra here, and the excess spectra will be given little bit above. It is called off resonance. So when it was given, we need to continue from this. If it is 10, yeah, the starting point is 10, 11, 12, something like this. So we need to count like this. So if it is not fitting on the one page, then we will cut the spectra here, then we will continue here. Okay, right. So carboxylic acids generally give a broad peak like alcohol P, OH, or amine OH. Sometimes carboxylic acids are not soluble in CdCl3. So that time what we will do, we will add small amount of deuterated sodium hydroxide. Deuterated sodium hydroxide, small amount. So when we add a base will pick up the proton from carboxylic acid. Okay, so to improve the solubility of carboxylic acids in CdCl3, what we will do, we will add small amount of deuterated sodium hydroxide so that it will get dissolved in the CdCl3.